Alright, welcome to the second video on this playlist thing. So let me remind you about what we're going to do today and what we did last time. Yesterday we took a look at congruences. Remember the mod thing with the 3 bar equal thing? Yeah, we did that. Now we're going to learn about group theory. So what we will do at the very last video is we're going to try to combine what we learned from group theory and what we learned from congruences, and we're going to try to put them together in order to figure out how Fermat's little theorem actually works and how to actually prove it. So right now will be an introduction to group theory. And I'm just gonna write it on top over here, group theory. Well, what is group theory? It is the study of groups. What are groups? Groups are structures that consist of a set of elements and a binary operation. So that's not the full definition. Structures that consist of a set of elements and a binary operation that satisfy 4 rules. Alright? But we'll be taking a look at this next time. I mean, like in a couple minutes. We're going to be talking about what this actually means first. So it's a structure that consists of a set of elements. What are elements? Elements can be any mathematical object. It could be matrices. Yeah, I think that's the right way to say it. Matrices, it can be coordinates, it can be vectors, or it can just be simple numbers. We won't be dealing with the complicated things. We'll just be dealing with numbers. So for the purpose of this video series, we're just gonna say a set of elements, just to simplify things. I mean, I just repeated the same thing. A set of numbers, just to simplify things. Alright, second complicated word, binary operation. What is a binary operation? Well, from the number, god damn it, from the 2-letter word bi, meaning 2, it is an operation that uses 2 numbers to create another number. Now in this definition, we're using numbers, but again, like I said, it can mean anything. It can be an operation that takes 2 matrices and combines them and forms another matrix, like when you multiply matrices together to get another matrix. So right now we'll just be dealing with numbers instead. So what is an operation that you can do to 2 numbers to get another number? And it's not too difficult to figure out. There are lots of examples actually. One of them is addition. You can add 2 numbers together to get another number. You can add A plus B to get another number C. Addition is a binary operation because it uses 2 things to get another thing. Something that is not a binary operation is, for example, sign. You can take the sign of a number to get another number, right? But this thing only has 1 input, as opposed to addition, which has 2 input. This is a binary operation, but this is not a binary operation. It only has 1 input. So there's how you figure out if any mathematical operation is binary or not. Alright, before we take a look at the 4 other rules that I've mentioned briefly before, we're going to take a look at what this could actually be, because this is just a definition. Alright, this is just a sentence. But what is an example of a structure that consists of a set of numbers and a binary operation? Well, why don't we take a look at our number system, this thing, right? 0, 1, 2, -1, -2. Why don't we take a look at that number system, right? Of course, it extends further this way and extends further that way. Right, so this is a structure. It consists of a set of numbers, and there is a binary operation. You can add two numbers together, 1 plus 2 to get 3. You can subtract numbers together, that is also a binary operation. You can multiply numbers together, that is also a binary operation. So this thing is an example of a structure with a set of numbers and a binary operation, but it is not a group, not yet a group. It needs to satisfy 4 conditions, and we will go over that right now. The first condition is closure. What does closure mean? It means that given a set of numbers and given a binary operation, when you use a binary operation, you're always going to end up with the same set of numbers. Alright, so let's take a look at this example over here. You can take any two numbers together, let's say 100 and 50. You can add them together with a binary operation. You're going to get 150. 150 is still within the set of numbers that we have defined. It is still within the same structure. It's just further ahead that way. You can have 5 and -100. You're going to add them together, you're going to get -95. That's going to still be part of the same number system, right? So closure, that's what it means. You take two numbers, you're always going to end up with a number that is still part of the same set. This is our set here. When you add two numbers, you're still going to get the same number from the same set. Alright, so that's number one, closure. I'm gonna write it here so that you can still remember if you forget what the first rule was. Second rule, that is associativity. What does associativity mean? It means that if you take any three numbers, right, let's say A and B and C, if you use a binary operation, again, let's take the example of addition because that's a really basic one. And if you add a bracket over A and B, is this going to be equal to A plus B plus C, but with brackets over here instead? If this is equal, that means it is associative. And obviously, this thing is equal, right? That means that addition is associative. Let's take a look at an example which is not associative. So let's just get rid of the addition and use a different binary operation instead, and let's see whether that yields an associative property or not. Let's use minus instead. Right, so A minus B minus C, that's same as A minus B minus C. We can ignore the bracket there, it's all fine. But over here, we can't just ignore the bracket. The negative can distribute inside, and that becomes A minus B. Negative and negative becomes positive. And you'll see that this thing is not equal to this thing. This means that subtraction is not associative. Therefore, if you have a group that has subtraction as a binary operation, you can immediately say that it is not a valid group. While if you have a group under addition, then, well, it is associative. It could become a group, but you would have to check the other properties. So that is what associative means. Some binary operations are associative, others are not. Some structures are associative, so other structures are not. So I'm going to write that here, associativity. And we move on to our third rule. Our third rule is identity. what do I mean by identity? What I mean by identity is there must exist a number within this set that satisfies the following property. We will call this specific number E, alright? There must exist a number E that satisfies a following property, and this E is within this set of numbers. So one of these numbers satisfies a following property. That is, if you take any number and add it with this specific number, it's going to do absolutely nothing. Alright? So I chose addition as a binary operation here as an example. So what do you think the identity is within this set of numbers? What is the identity here? Does this number exist? It could not exist technically. There could be a structure where the identity doesn't exist, but does it exist in this case, in this number system? Let's think about it. Give you 2 seconds because it's really not that difficult. 1, 2, alright. E is 0. Why? If you add anything to 0, wait. Oh god damn it, I screwed it up. I screwed it up so bad. Alright. If you add A with this number E, it's gonna do absolutely nothing to A. So what I meant to say here was A, not 0. Bad screw up, sorry. But what is E? E is gonna be 0. Why? Because if you add any number A with 0, that's gonna absolutely do nothing. 0 has that property. It is the special element within this set of numbers that we call the identity, because it has the property that it does absolutely nothing when you use it to add. But sometimes E can be a different element, a different number basically. So let's use the case where we have multiplication instead, right? So what is E now? With a different binary operation now. We're using a different binary operation. Addition was just an example. What if we have multiplication? What is the identity there? Again, I'll just give you, I don't know, 3 seconds. 1, 2, 3, okay. E is 1. This number does exist within the number system here. Therefore, the identity exists for the multiplicative binary operation. It also exists for the additive binary operation. So this number system looks good so far, on its way to becoming a group. It just needs to satisfy one additional property. Right, so identity is covered already. It is the number that does absolutely nothing when you use a binary operation. And again, we're gonna write that here, identity. Alright. Fourth one, and the final one, is inverses. What do I mean by inverses? What I mean by inverses is if you take any number from this set over here, and we'll call that number A, then there must exist an element known as A inverse. And A inverse has the property that whenever you add it with A, you're always going to get the identity. The identity in this case is 0 because we're using addition. When we're using multiplication instead, we should change the identity into 1. But in this case, we have addition, so we can just change the identity into 0. So we need to figure out if this thing exists or not. If we pick a number A, does this thing exist? Well, let's use an example, okay? Let's pick the number 2, okay? So A is 2. 2 plus A inverse is 0. Does this number exist? Well, yeah, -2. Why? If you add 2 with -2, you're definitely going to get 0. You're going to go back to the identity again. And same thing with any number, basically. If you have the number 5, then the inverse exists. It's known as -5. If you have 6, the inverse exists, it's -6. Well, let's take an example if we switch the binary operation up again. Let's say it's multiplication this time. We can't use subtraction or division because it is not associative. The order matters when you divide and when you subtract. That's why we can't use it, because that wouldn't form a group. If it's not associative, it's not going to form a group. So multiplication and addition are the only examples that we're going to be using. Alright, so what is the identity when you multiply things? Remember, it's 1. So let's just write 1 here and write 1 here. Alright, does this number exist? 2 multiplied by some number is equal to 1. Does this number exist? Well, yeah, it's 1/2. It's here. 1/2 does exist, and so the inverse exists for any number. If you have 3, the inverse is 1/3. If you have 4, the inverse is 1/4. And thus, this number system completely satisfies all 4 conditions that make it a group. So that's an easy example. But do other things form groups as well? Because we just took a look at our regular old number system. That's not very exciting. It makes for an easy example, but it's not very exciting. So let's take a look at a different structure that forms a group. Alright? So let's consider this structure here. Alright, it is a structure that consists of a set of numbers. What is the set of numbers? It is 0, 1, 2, and 3. In our previous example, the set of numbers is the set of all numbers. Yeah. So right now, we only have a finite set of numbers. We only have 4, 1, 2, 3, and 4. Whereas the previous example, we had literally every number imaginable, okay? Well, except for the complex numbers, basically, but literally any number imaginable. That is our set. Now we have a finite set. The other example before, we call it an infinite group because it has an infinite number of elements, whereas this would be a finite group because it only has a limited number of elements or numbers. Alright, so does this form a group? Well, wait, we have to define a binary operation first. And again, let's just use addition. Addition is our binary operation. So let's go through all these 4 rules again, starting with closure. What happens when we add 2 elements together? Well, addition might not work like we imagined it to, because if we think about it, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and if we just follow the same pattern, 3 plus 1 is 0. Now that's where things start to get interesting. Because we have a different structure, we have a different property, a different set of rules that this number have to follow. It's like water filling a glass. It depends on the shape of the glass, how the water will flow and fit itself in. So the numbers just follow the flow of the structure. And since our structure acts this way, the numbers behave in this way. Pretty weird, but it is what it is in this cycle structure. So let's figure out closure. Let's try to add numbers together and let's see what we get. Let's just try an example. Let's try 2 plus 3. What is 2 plus 3? 2 plus 3 is 2 plus 1 plus 2 plus 3. 2 plus 3 is 1. Okay, what's 1 plus 2? Well, that's 3. What's 3 plus 3? Well, that's 1, 2, 3. 3 plus 3 is 2. And, well, it's not like the addition that we all used to know, but it is how this thing works. and I think it is closed. Why? Because I don't think there is a way that you can add numbers together in order to get out of this loop. You can see that this loop is continuous no matter what you add. Basically, like whenever you add something, you're going around the circle, right? So no matter how many times you add, no matter what you add with, you're just going around the circle still. So you're not going anywhere, basically. You're always going to end up with elements from the same circle, right? All of these values, they're all part of this circle. You're never going to get anything outside of it. That's why this structure is closed. It satisfies closure. We'll give it a check mark there. What about associativity? Well, we know that addition is associative already, and we've proven that, just as we've proven that subtraction is not associative. Therefore, we can immediately just give this a check mark as well. What about the identity? Does the identity exist? Well, again, our binary operation is addition, and addition's identity is 0, and 0 does exist here. If we add 3 plus 0, that's going to be 3. If we add 2 plus 0, it's going to be 2. If we add 1 plus 0, it's going to be 1. 0 does absolutely nothing. And even though we have this new addition defined, this alien type of addition, 0 still satisfies the role of the identity in the fact that whenever you add it, even if this addition is the weird addition, it still satisfies the property that the numbers don't get affected in any way. So we can give that a check mark as well. What about the last one? What about inverses? If we have a number, do we have the inverse? Does the inverse exist? Let's take an example. 1. Does 1's inverse exist? What's the identity? The identity is 0, because like an inverse plus its element, when you add them together, it's going to give the identity always. That is the property of the inverse. So does 1 have an inverse? Alright. So let's try to go around the circle. Well, 1 plus 1 plus 1 plus 1 is 0. So I guess a inverse is 3. 1 does have an inverse. What about 2? Does 2 have an inverse? Well, let's try to go around the circle again. 2 plus 1 plus 2 goes back to 0. I guess 2 plus 2 is 0. That means the inverse of 2 is itself 2. So this number does exist because this number is 2, and 2 exists because it is part of our number system. This new number system, this new circular weird number system. And that goes the same for any number. No matter what size this circle is, if you pick any number, you can keep adding, and going around the circle, and you'll eventually reach 0 at some point. And that means that you can add a number of times to get back to 0. Let's say you add 7 times to get back to 0, you can add 3 times to get back to 0. Well, that depends on the size of the circle. But you're always guaranteed to land back to 0. Therefore, an inverse always exists because you can always add that much to get back to 0. Right, so that's cool and all. Inverses do exist, and that means that this weird number system also apparently forms a group under the binary operation of addition. Alright, cool. So you might be wondering, well, where is this going to? What's the point of all of this? Well, I can't say that for sure yet, because if I say that like definitively now, I'm gonna go on like rambling for 30 minutes or something about the applications of group theory, but you're just gonna have to bear with it for now, okay? I know all of these seem pointless, but within 2 more videos, you're gonna take a look at why this could potentially be important. But for now, we have we know how to identify groups. We've taken a look at 2 examples. So now why don't you test your skills a bit. I'm gonna give you a surprise quiz. Woo. Alright, we're gonna give you questions. Just simple, really. It's 3 questions, and it's just a yes or no. Is it a group? Is it not a group? We're gonna start with the odd numbers. And we're gonna restrict the binary operation to only addition. Right? Addition. Second one, even numbers. Same binary operation, by the way. Addition 2. Third one, we're gonna have a different cycle now. But take note at the key difference. It has a 1, so we completely got rid of the 0. And we just have 1, 2, and 3, and 1, 2, and 3, and like that again. So before it was 0, 1, 2, 3, 4, and now it was 1, 2, and 3. Does this still form a group? Well, that's for you to figure out. And again, the binary operation is addition. Although this is not the same addition as this one here. This is the weird addition, the one where 3 plus 1 is equal to 1, according to the structure. So just, well, believe in the structure, believe in what the numbers behave as according to the structure, and that is how addition works, apparently, if things work this way. But yeah, well, I'll leave you to it, so you can pause the video, and whenever you're done, you can get back. But for now, I will directly leap into the answer. So pause, like right now, or don't. I mean, if you don't bother to. Let's take a look at the first example. Odd numbers. Do they form a group? Well, we can go over the 4 rules. And immediately on the first rule, we're going to see that odd numbers break the first rule. Why? It's not closed. What happens when you take 2 odd numbers and you add them together with the binary operation? What happens when you get 2 odd numbers, add them together? What's 3 plus 1? That's 4. What's 4? That's definitely not a part of the odd numbers. It's outside of the group. You add 2 things together and you get something that is outside. That's not what's supposed to happen. So odd numbers does not satisfy closure. It is not a group. Another important note on why this does not form a group is it does not have an identity. What's the identity under addition? It is 0. 0 is not part of the odd numbers because 0 is an even number. Therefore, it also does not satisfy the identity here. Alright, next. Even numbers. Do they form a group? You might be convinced or persuaded to think that, oh, if the odd numbers don't form a group, then the even numbers must also not form a group. But that is actually not the case. Because what happens when you take an even number and you add it with another even number? You're always going to get an even number, no matter what it is. So closure is satisfied. What about associativity? Well, we're talking about addition here, and addition is always associative, as we've said before. So that's check. What about the identity? Well, we said earlier that 0 is part of the even numbers and not the odd. So that's check as well. What about inverses? Does the number 4 have an inverse? And remember, inverses add together to give the identity element, which in this case is 0. Does this element exist, and is it part of the same set? Well, yeah, it's -4. And -4 is an even number as well, because it is divisible by 2. So yeah, you can tell that the even numbers do form a group because all of these 4 are satisfied. What about the last one? Well, the last one was different from the example we took a look at. What's the main difference? It doesn't have a 0. Why is that important? Because 0 is the identity. And since it does not have the identity, it does not form a group. So our only group in this case is the even numbers. If we got all 3 of them right, then I am very happy because that means that you've learned something and you understood it pretty well. If you got 2 out of 3, that's still good. If you got a lot of mistakes, well, that's fine too, because at least now you know why you're wrong and you can learn from it. Right, so that's going to be it for this video. It's just an introduction of what groups are. Now you can tell whether something is a group or whether something is not a group. And next episode, should I really call it an episode? Whatever. Next, we're gonna talk more about groups, I think, because I'm not done talking about groups yet. This is just a basic introduction, and in our final video, we're gonna be, like I said, combining the knowledges together in order to finally prove Fermat's little theorem. Anyways, that's it for now. See you.